All right, we're going to look at the derivative as a function. This is going to be the beginning of OpenStax section 3.2. Okay, the derivative viewed not just as an individual number, like a slope for a particular tangent line, but rather as a function in its own right. Here's the definition we take. The derivative of a function f of x is another function called f prime of x, right? So this would be a new function. F is one function, f prime is a separate function. They're related, they're not the same thing. And this new function outputs the slope of the tangent line to f. I didn't mention that, but f, right? At the input value x. So it's related, f prime is related to f, right? It's just a new function, right? And if you give it an input, then it spits out the slope of a tangent line for the original function that it is the derivative of. Okay. And the definition is just this here. This is just the definition we've already seen, except you'll notice that instead of having a constant here and here, we have x, a variable. So there's two variables involved in this difference quotient, and this difference quotient here. There's two variables, there's x and there's h. We're taking the limit with respect to one of those two variables, and so that variable is dealt with. It's not going to be there any longer after we evaluate the limit, but we will still have the x left over as genuine variable it's going to stick around. The final expression when we're done solving this limit problem is not going to be a constant number. It's going to be an algebraic expression of x. So let's do this example with x cubed. Okay. First of all, we're going to need to write f of, well, we have f of x. We're also going to need to know f of x plus h. And remember, when you evaluate a function at some input, the input replaces x. So x would be there, x cubed, and so x is getting replaced by x plus h. I'm going to color code these again. Let this be the red one, and this will be the blue one. Okay. So now what I want to do is I want to copy this expression up here. This is where the red is going to go, and this is where the blue is going to go. Okay. So for this f prime of x will equal the limit as h approaches 0, and then we can have x plus h cubed, the red, minus the blue, x cubed, and then all over h. Okay, so this limit looks a little bit different than limit because it has these two variables floating around, h and x. That's okay. We approach it exactly the same way we did with the others. We're still going to apply some algebra manipulation to try to isolate, try to factor out an h in the numerator so that we can cancel that h in the denominator. Very similar to what we did in the previous video, where it was done in a specific. Okay, so what I'm going to do is I'm first going to just expand the cube in the numerator. I'm going to kind of use a shortcut for this. Comes from the Binomial Theorem. You can do it the long way if you want and confirm for yourself that this is what you'll get. So that x plus h, if you cube it, you're going to get x cubed plus 3x squared times h plus 3x times h squared, and then plus h cubed. All of that is equivalent to what was in red originally. Those are the same. Okay. So now I'll take that and subtract from that this part that was in blue. And I've still got to subtract x cubed. There we go. Now I don't need to bother writing any parentheses. I don't need to bother writing parentheses here because there's no need to distribute the negative. This is only one term that I'm subtracting. I also don't need to bother writing parentheses here because it's just not necessary. There's nothing to distribute there either. So I'm omitting all the parentheses in the numerator. That's fine. in our denominator, we just have h. We haven't multiplied the numerator and denominator by anything, so all we're doing is just manipulating the numerator so far. But very quickly, we can see something nice happens. We have an x cubed here and an x cubed here. This is positive, this is negative. Those two terms are going to cancel each other out. Lovely. So now our numerator contains only the terms 3x squared h plus 3x h squared plus h cubed. And similar to what happened in the last example, every term that remains in the numerator has at least one factor of h. So we can factor out that h, at least one of them. That's all we need is one. And so what's left over is going to be 3x squared times no h's, and then plus 3x times 1h, because there were 2 originally, and then plus h squared, because there were 3. I'm taking one h factor out of each of those terms. It's all still divided by h. Now, as you can see, this in red, h over h cancels out. All right. So now we have the limit of 3x squared plus 3xh plus h squared, and we are taking the limit as h approaches 0. So we're going to do direct substitution. That's going to be 0. That's going to be 0. We get 3x squared plus 0 plus 0. Just that. So like I said, the final answer here is a expression, an algebraic expression. It's a function. This is the function f prime of x, okay? And now if you say, for example, if you want to know what's going on here. If you want to know, say, tangent slope at like x equals 2, for example, all you have to do is take this function, this f prime of x, and evaluate it at 2, which means replacing the x with 2. 3 times 2 squared. That's 3 times 4, or 12. So that means that the slope of the tangent line at x for the function, for this function, right? All of this is relative to this particular f of x, x cubed. That slope is 12. So you can do this at any x value you want, because you have a rule that gives you the tangent slope at any x value that you want. Okay, now I've come over here to the right side of the screen. I want you to try this on your own. I want you to try the same process of evaluating the limit of the quotient to find the derivative of the function as a function on its own. With each of these examples, 1, g of x is x squared plus 3x plus 1, and 2, h of x is 1 over x. Okay, so we're going to find g prime of x, okay, and then find h prime of x. Okay, pause the video now and try it on your own. Have you done it? All right, I am going to tell you the answers. I'm not going to show you the full solutions, but I'm going to tell you the answers so you can check the work. If you got it wrong, see if you can figure out what went wrong. You can always talk to me in office hours if you want some feedback on your work. I'll tell you the answers. G prime is going to be 2x plus 3. Okay, that should be your derivative function. For h prime should be -1 over x squared. So, 2 answers. And if you're wondering how I knew those answers so quickly, it's not actually because I solved them on a piece of paper on the side. I didn't actually do that. I did them in my head, but I didn't do them the way that I've shown you so far. it turns out that what we're doing over here, this is using the definition of the derivative. This is the initial way that we define the derivative. This is how all derivatives can be approached using the limit of a different quotient. However, it's cumbersome. We don't want to have to be doing this all the time. There are shortcuts, lots of good shortcuts. And in fact, by the end of the semester, you won't really be doing it this way any longer at all. You'll pretty much just be using the shortcuts. Occasionally, we do have to resort back to doing this, and we're going to prove all of our shortcuts by doing something like this. But the shortcuts themselves end up being the main strategy for finding derivatives. And we'll be learning those very soon.